This resource is the first in a 5-part series on vectors. Part 1 defines vectors. The component form for a position vector is presented with an example. We also discover how to find the magnitude of a vector. Part 2 considers basic operations with vectors. We look at adding and subtracting vectors in component form with examples. We also consider scalar multiplication of vectors. Part 3 considers writing the vector in terms of its magnitude and direction. Part 4 describes how to find the resultant force when two different forces act on the same object. Part 5 looks at the dot product of vectors, looking at multiple examples, including a word problem. In mathematics, we define a vector as a directed line segment. This means a vector has a specified finite length, called the magnitude of the vector, and a direction. If a value has only a magnitude but no associated direction, it is called a scalar value. A good example to show the difference between a vector and a scalar is to consider the difference between speed and velocity. Speed is a scalar value. It tells how fast you are going. Velocity also describes how fast you are traveling, but velocity is a vector measurement. Velocity requires a direction to be traveling. So you can describe your speed as 50 miles per hour, while your velocity is 50 miles per hour due south. Because vectors have directions, there is a start and an end to them. The starting point is called the initial point, and the end is the terminating point. But how exactly can we give a name to vectors? To start building the equation for a vector, we first consider two important unit vectors. Like with much of mathematics, we start by looking at the Cartesian plane, normal x and y coordinates. We define boldface I to be a unit vector in the x direction, and boldface j to be a unit vector in the y direction. Using these two unit vectors, we can describe any vector in the xy plane. Consider a vector v. To start, let's think of the initial point as the origin, or the point 0, 0. Our terminal point will be the point a, b. Then the component form of the vector v, written in terms of I and j, would be v equals ai plus bj. How can we find this component form if we do not start at the origin? Suppose we have the initial point x sub 1, y sub 1, and the terminal point x sub 2, y sub 2. How can we find the position vector that is the equivalent to this vector? That is, how can we find a position vector with the same magnitude and direction? To do so, we subtract the coefficients for I and j. The position vector equivalent will be the quantity x sub 2 minus x sub 1 times boldface I plus the quantity y sub 2 minus y sub 1 times boldface j. An important thing to remember is that we subtract in the order terminal minus initial. Let's look at an example. Suppose our initial point is 4, 7, and the terminal point is 6, 11. What is the equivalent position vector? Plugging into the formula, we have 6 minus 4 times I plus 11 minus 7 times j. So the position vector would be v equals 2I plus 4j. We have talked about the magnitude of a vector. We defined it as the length of the line segment. But how exactly do we find that value? If we have a position vector, then the magnitude of the vector is found by taking the square root of the quantity a squared plus b squared. Let's take a look at an example. Suppose we have the vector from initial point 9, 2 to terminal point 4, 14. First, we want to find the equivalent position vector. Then we will find the magnitude. Plug into the formula. Our position vector is v equals negative 5i plus 12j. Now we can plug in and find the magnitude of the vector. We have the square root of the quantity, negative 5 squared, plus 12 squared. After solving, this means that the magnitude of our vector is 13.